Hi, welcome to the dynamics tutorials. So in this case we're going to have an impact with an immovable object, and we're also going to use work and energy, or conservation of energy in this case, mix that in with conservation of momentum to solve this problem. So we have a sphere that's attached to a rod. The rod has negligible mass here, but it has a length of 1 meter. And then the sphere has a negligible size, but has a mass of 1 kilogram. It's starting from rest here. We drop it. It falls down, strikes 1 meter below the initial height, and then it rebounds to some kind of final height. So we want to find out what that final height is. So we can use conservation of energy to figure out what velocity it has right before it strikes. So our initial kinetic energy plus our initial potential energy is equal to our final kinetic plus our final potential energy. If we establish a y equals 0 datum plane, so we have to do that and establish where we have y is equal to 0. So if we do that here, then we're starting from rest and we're starting from our datum. So we have no potential, no kinetic energy. And then right before it hits, we'll have our kinetic energy, 1/2 mv squared, and then we'll have our potential energy of weight times y. So plugging that in, we'll have 1/2 our mass times our v squared, and then our weight, 9.81 newtons, times our -1 meter, because now we're below the datum by 1 meter. Solving this, we get a velocity of 4.429 meters per second. We'll notice that the velocity is going in the negative x direction, so I'm going to call it negative 4.429. Now we need to kind of think about our free body diagram. So that would be our free body diagram for the mass as it's falling. And then we also need to think about our impact diagram. So right as it hits, we've got the wall, and we've got our particle like this. And so the motion is in this direction, and if we draw a line through the mass center in that direction, then we can establish our line of impact, which is our x. And then you can see that your plane of contact, so the tangency through the point of contact would be here, and this would form your y-axis. Again, remember with the plane of contact, it really is a plane, but you're looking on it on the side, so that's giving you just the one axis. In this case, all of our motion is in x. Of course, there is the weight and the tension, but this impact is occurring over such a small time scale that we don't need to even consider those forces. So we'll do our linear momentum conservation equation. So we've got our mass of the ball, our sphere rather, times the initial velocity of the sphere, plus the mass of the wall times the velocity of the wall, is equal to the final mass of the sphere times the velocity of the sphere, and the mass of the wall times the velocity of the wall. Well, we've got a problem here though, because the velocity of the wall is essentially 0 before and after impact, but the mass of the wall is essentially infinity before and after impact. And so when we're multiplying 0 by infinity, we don't really know what that result is going to be. So this equation basically is just not helpful for us whatsoever. So we'll instead use our coefficient of restitution equation. And now we don't have the masses in here, we just have the velocities of the wall. And so both velocities of the wall are approximately equal to 0. And so we just set them equal to 0. So that gives us then negative v2x divided by our initial negative x velocity of 4.429. Plug that in down there. We can solve this equation then for v2x, and we get positive 2.215. So that means we've hit, we've rebounded, and now we're going back up. We can do a final conservation of energy to see how high we rebound. So we'll have our initial potential and kinetic energy before the impact. I'm sorry, after the impact. And then we'll have our potential and kinetic energy here then while it's momentarily stationary at the peak of its height. So here's our velocity that we just calculated with the 1/2 mv squared term. There's our -1 meter location that we start out at right immediately after the impact, and then that's going to then a 0 velocity, so no kinetic energy, but a potential energy term that's the weight times the final y position. So we solve for the final y position and get 0.750 meters, and so that means its final height will be 0.750 meters below its starting height. Thanks for watching.